Hello, in this module, we are going to talk about a very important concept of called as Maxwell equations. So Maxwell equations basically help us to understand the behavior of electric and magnetic field. So we have E vector indicated by this, or let's say this sign, okay, and we have B vector indicated by this or this symbol. So let us understand what are Maxwell equations in detail, how they help us. So basically Maxwell equations helps us to explain how the electric and magnetic fields interact with each other and how their interaction with the charges and the currents, charge indicated by Q, current indicated by I. And this also Maxwell's equations tells us how the EM wave propagates through the space. So now, first equation, Maxwell's first equation is a Gauss law for an electric field. So that's the first equation. So let's understand in detail what is this equation. Maxwell's first equation is, imagine you have a volume or a simple cube and there is a charge in this. There is a charge here. Okay, it could be a positive charge or it could be negative charge, depends on that. So obviously if there is a charge, it will experience or electric field component will come out of it. The electric fields will come out of. So let me take you to this figure. So there is a closed surface indicated by the sphere or say the round, and there is a positive charge sitting over here. So this positive charge, when it is in the static position, it is not moving, it will radiate the electric field around it, indicated by the arrow. So close to this charge, within this closed surface, the electric field is stronger, and as we move away from this charge, the electric field is weaker. This we know from the theory of electrostatics. Now, more the lines we draw here indicates how strength of the electric field, how strong is the electric field. Okay, so the first Maxwell equation, which is the Gauss's law, tells us the total electric field lines coming out of this closed surface, arbitrary closed surface. It tells us what is the strength of that electric field coming out of this surface. So let's have a look at this picture now. Let's have a look at this picture. So Gauss's law is telling us in this closed surface, again, there are two charges we have placed. This is the closed surface. And we have placed two charges. One is positive charge, one is negative charge. We can also take this example where only there is a one charge. But now we are focusing on this one. So we know that from the theory of electrostatics, the positive and the negative charges, if they are placed close to each other, they will experience the electric force, or electric field lines will emanate from the positive charge, originate from the positive charge, and they will end up to the negative charge. But some lines are also coming out of this surface. So the first Maxwell equation, which is Gauss's law for electric field, states that the flux of the electric field out of this closed arbitrary surface is proportional to the net electric charge enclosed by the surface. Okay, so whatever the lines are coming out of this electric field, whatever the lines are coming, that is nothing but the total electric field, or in short word, flux. So that flux, the strength of that flux or magnitude of that flux is proportional to the charge enclosed by this closed surface. So that is your first equation. But how to express it in mathematical form? Okay, it is that strength of the flux or the magnitude of the flux is given by this equation. So it is simply says this total electric line coming out of this closed surface, or simply one word, flux, is equal to charge times 1 over epsilon 0. We can also call it as a 1 over epsilon 0 epsilon r. So 1 over epsilon 0 is a constant, or 1 over epsilon 0 into epsilon r is a constant, multiplied with the total charge. So basically, if we take that 1 over epsilon 0 is a constant, so this flux phi e is proportional to the charge multiplied by this constant. Okay, so remember, first Maxwell equations tells us the total flux coming out of the any closed surface is proportional to the charge enclosed by that surface. Simple, very simple. Let's move to the next slide. Again, we are at this figure, and there are two ways we can represent this first equation or first law, which is Gauss's law for electric field. One is the integral form. How to express this mathematically? So I have already told you, let's take any volume. For example, you have this volume right here, and there is a charge sitting over here. Only one charge. In this picture, we have shown two charges. So positive is attracting to the negative. There is this one, but some lines are coming out of this closed surface. So there is this surface, arbitrary area. Any small area we can take of this surface, of this volume. So the electric flux, which is phi e, is basically can be calculated by taking the surface integral of this particular area, just small area of the electric field. So electric field is coming out of these charges, from these charges, or go for this picture, and these lines are coming out of it. So we say that this flux will be double integral. You see, as indicates the surface area of that from which the electric field lines are coming out, and surface integral of the electric field into dA. So that's the dot product. Okay, so E is the electric field and dA is the small, is a vector represent the small area of this volume out of which the electric field lines are coming, and the dot represents the dot product of these two vectors. So electric field is a vector, dA is a vector, take a dot product. So this is the very first equation of Maxwell's Gauss law in the integral form. Can we represent it in the differential form? Yes. So again, have a look at this picture. Let's say there is a volume, and in the volume we place the small positive charge, and we take the area, small area indicated by this circle is the small area out of which the lines are coming out. The lines are coming out, and that is nothing but our flux. So that flux can be linked to the charge density. So this says that del dot E is the divergence of the electric field. Divergence means lines are coming out, diverting. That's why we say that this divergence, which is the dot product del dot E, is proportional to the 1 over epsilon multiplied by the charge density. There is a single charge here, so there is a charge here. Okay, remember we also had written in the previous slide, this equation was 1 over epsilon multiplied by the Q. The same equation is here. So instead of Q, we write here rho. So del dot E is the dot divergence of the E field. Epsilon 0 is the vacuum permittivity, and rho is the volume charge density. It means in that particular volume, the charge is sitting here, and these lines are coming out, and we take just a small area, and from that area how many lines are coming out, which is nothing but the flux. That flux is proportional to the what is the total charge enclosed in that volume. Okay, so this divergence del dot E of the E field at any given point to the it relates, the first law relates the diversion of electric field at any given point to the total electric charge density at this point. And epsilon 0 is the constant permittivity of free space. So what's the application of Gauss law? This basically helps us to find the total distribution of electric charge. So any surface, any volume, sphere, cube, or any volume, there are, let's say inside there are charges, and the field lines are coming out of that volume. through some area, and we can calculate what is the total charge enclosed in that particular volume. So that's the end of our first law or first Maxwell equation.